Hello and welcome to today's PIR live event webinar brought to you by Partners in Research Canada, the Canadian Space Agency, and the Institute for Earth and Space Exploration. My name is Stacey Joyce and I will be your host. If you're joining us live, remember that you can ask questions anytime by clicking Q&A near the bottom of your screen and typing your questions into the pop-up window. I will relay these questions to our guests later on, but you can certainly type them out as you think of them during their presentation. Speaking of our guest, today's guest is Gavin Tolometti. He is a PhD candidate at the Institute for Earth and Space Exploration and a GradCast committee member in the Department of Earth Sciences at the University of Western Ontario in London, Ontario. Thank you for joining us, Gavin. I'll let you take it from here.
Oh, thank you very much. So I think if everyone can see the presentation at the moment.
Not quite yet. I think you're just going to have to do the screen share again.
And
I stole it for the preview. There we go. Now we can see it again. We've just got a little grayed out area near the top right there. I don't know if you have anything on top of that window.
I don't think so at the moment. Let me see. I think it should be a bit.
Okay.
Okay. Yeah.
That's good.
Okay, so for you guys, I'm going to quickly, before we talk about the junior astronaut activity for today, I want to quickly talk to you about how I get to study the surfaces of some planets and moons, in particular our very own moon. And one way that I and other scientists in the planetary science community and in science in general use different types of light. So I don't know if most of you might be familiar, but if not, this is the light spectrum. So different types of light or radiation we can use to view different features on planets and moons. For example, we can use X-rays and gamma rays. So you're probably familiar with those with radiation. We can use those to look at different types of structures and compositions. We can use visual light, so the light that our eyes can see, just to see what is actually on the surface. And then we could also use different types of light used in radio, which they're a lot longer, but it's signals that we can't physically see ourselves, but it's the signals that we can use to operate radios and to send information. So for me, I mainly focus on radio and microwaves. So again, with microwaves, it's literally the same type of radiation used in the microwave in your kitchen. And what this light can do is something that optical, or the light that our eyes can see, can't do when looking at different planets and moons. So the light that we can see can't see through cover such as clouds and very thick atmosphere, which is a problem in planetary science because we want to see what's on the surface. So for planets like Venus and Saturn's moon Titan, this poses an issue. Radar has an advantage using microwaves and radio waves that its signal, as you can see from the little GIF at the bottom, it's able to penetrate through clouds and atmosphere and then interact with the surface. And this can allow us to see different features. And for me, two types of features I focus on are lava flows produced by volcanoes and impact craters, which is what happens when a meteorite or a comet strikes the surface of a planet or a moon. And this is kind of give you an idea of what they look like. Lava, as you've probably seen from different clips when Hawaiian volcanoes erupt. And craters, you can see them covering the surface of our own moon. So they're really good examples. Actually, the one on the right is a crater that's actually from Mars. So volcanic eruptions, the reason for me why I focus on them and use radar to study them is because we want to be able to understand what type of eruptions occurred on other planets and moons besides our own planet. And volcanic eruptions can range from different types. As you can see from the far left, we have this one called a Pinion eruption, which is just a huge plume of smoke would come out of a volcano. And we can get some that are less intense in terms of producing smoke and ash. You can get ones that we call Icelandic eruptions, where we just have lava creep through the crust and break out of a giant crack, which we would call a fissure or a rift, and just cover the surface in lava. So by studying the lava flows that are formed or other volcanic products that are produced by these volcanoes on other planets and moons, using radar and other types of light, we can understand how they formed millions to even billions of years ago. Because most planets besides our own planet and one moon in Jupiter called Io is still volcanically active. So this just gives you a different idea of what they can look like. So the video on the top right can just show you how lava actually flows while it's still hot. And the one on the left is a flow from the Kilauea Mount volcano on Hawaii, showing how it can form these channels that move away from the volcano itself. And at the bottom are pictures I've actually taken when I went to the field. When I went to Idaho in the United States, was a huge lava field there called Craters of the Moon. And also in Iceland, the new, pronounced as the Holarun eruption, which happened in 2014. So you can see how much they actually differ in terms of their surface texture. Get some that are what we call smooth, but it really means that it's not very sharp or jagged. And then we move to very rough surfaces, which can be covered in blocks that look similar to material you find at construction sites. So it's like a very treacherous and rough material. So we really want to understand how they formed on Earth, so then we can maybe understand how they probably formed on other planets, which have similar types of lava. And it just gives you an idea of what lava looks like in our other planets and moons in our solar system. So on the left, this is just an image from the Mars orbiting camera. And it is from a volcano on Mars called the Escries Mons. And these are types of flows. You can see them with the black arrows pointing them out, these huge kilometer scale lava flows covering the surface. And on the moon, sometimes if it's a full moon, you look at the night sky, you see those dark patches. So those are what we would call mare lava flows. And they're literally seas of lava. So if you can imagine an ocean, but instead of water, it's all lava. And that's what that would have looked like before it would have cooled down and created this black basaltic-like material on the moon. So I want to quickly transition from volcanism and move towards impact cratering, or impact craters in particular. So what's very unique about these structures is that they are found on almost every single solid body in our solar system. And I'm including Mercury, surface of Venus, Mars, the moon, Jupiter's moons, Saturn's moons, they're everywhere. So it's just the one geologic process or event that can happen all over our solar system. So it's one that we planetary scientists particularly like to study because if it happens everywhere, we want to understand how does it affect all these different surfaces on the planets and moons, and why do we see it everywhere? And maybe why some are more littered with craters and some aren't. Most of the answers to that is usually because of erosion, or they weren't formed in it during when there was a lot of impacts. And it's just as a couple examples of what some look like in our solar system. So the really big image, these are craters that are actually on one of the large Galilean moons on Jupiter called Ganymede. And on the top right, which is a very unusual one called Victoria crater, which actually formed on the surface of Mars. And actually look right in the center of the crater, you can see these little wavy patterns. Those are sand dunes. So they'd be sand dunes are actually similar to the ones you can see in the Sahara Desert here on Earth. And on the bottom right is one of my favorite craters on our moon, is called Tycho crater. And on a very good night, when the moon is full, you can actually see this crater from Earth with a good telescope, because it has these beautiful rays that come almost like emitting away from the crater itself. And that's material that's just been placed on the ground while the impact crater is forming. So that's kind of like a very brief introduction of what I do using different types of light, mainly like visual light, microwave and radio waves to study lava flows and impact craters on different planets and moons. So now I'm going to introduce you to the Junior Astronauts Initiative. So the Canadian Space Agency is recruiting students to participate in different streams, similar to what types of training that astronauts would receive. So we have the physical and health stream, we have the science and technology stream, and we have the communication stream. And the really good thing about the junior astronauts, if students and teachers can sign up for free on the website. If you type in Junior Astronauts Canadian Space Agency, it will take you straight to their website. And if a student can complete one activity from each stream, you draw in for the chance for either a science expert or a Canadian astronaut to come visit your classroom. And if you also complete all of those, you also have the chance to be selected to attend the Canadian Space Agency Space Camp during the summer. So I think if if teachers and students, when you go back home and get your parents to take you on the website, I would highly recommend you look at some of the activities, and I'm going to actually show you one of them from the communication stream. So actually, just to really backtrack, we also have a promotion for Girls of Science. So just to demonstrate the endless careers for women in planetary science and in STEM to get to have different careers, from doctors, mathematicians, flight controllers, and psychologists. So the Canadian Space Agency and the Institute for Earth and Space Exploration is highly promoting this and is really wanting to ensure that we have equality in STEM and planetary science. So this activity for today is the patch maker activity. So when you think of a patch, you would think of something made of fabric that gets sewn onto either your jacket or your backpack. For astronauts, they all have their own individual patch every time they go up to space. So they would design it based off either what the mission is about, what their inspiration and passion is for space or the mission, or something that they feel very strongly about, they want to send a message. So here's one example from recent astronaut who just Canadian Space Agency astronaut, David St. Jacques. His patch shows stars beyond Earth, and mainly the North Star. He's enlarged it to really make it stand out, and the compass rose, and he picked 4 colors signifying innovation. So it's kind of one example of idea of what David St. Jacques picked, and these are a lot of other different examples. You can also notice that not all of them are circular. Some are more oval shaped, some are square, and some can even be triangles and very irregular shapes. They don't always have to be perfectly circular. So we've got a couple examples, like the top left is from Dr. Roberta Bonda, the first female Canadian astronaut. She has the space shuttle that slowly emits out of the Canadian flag. We have David Williams with the bottom one with the STS-90. He has a picture of the Canadian Space Agency, the space shuttle, Canadian flag, and the medical symbol on the left. And there's all different types of designs you can have. So it can either be very detailed or very creative. And this is an example of what some students have already designed when we asked them to create their own patch. So on the left, the kids were asked to design a patch about collecting resources on the moon. And the one on the right is how they would get to travel to other planets beyond Mars and get back to Earth. So they just had Jupiter and a couple of the gas giants and had a rocket circling around the Earth, symbolizing going to the planets, but also coming back. So the activity would pretty much involve either individually, you would create a patch for yourself, and you get to pick any type of mission. You can even make up the mission as well. And you would create a patch that's meaningful to you. You have the name of your space agency, and you would also have your name on it, since it is your own patch. And after that, if with classes and each student creates their own patch, what you do afterwards, you would get into groups to create what they call mission patches. So along with each astronaut, they have their own patch, but they also have a patch representing the mission that they participated in. And it always has the crew members' names. So the one on the right has all 3 astronauts during the 58th visit to the International Space Station. The mission number is usually present, and again, a meaningful image. So this is Expedition 58, and then they showed the Earth below with all the lights from the different cities. Again, they had the compass rose, which is the light of the star shining out, and the passing of the International Space Station going over the Earth. So with that, you would design your own mission patch in groups, and you just have to make sure those 3 things are included in your patch. So I wanted to thank you again, and PIR for inviting me for this presentation. Are there any questions?
Thank you so much for that presentation, Gavin. It's really neat to see in these activities that there is a communication stream too, because I think that we forget that's part of training to be an astronaut. You must be able to communicate so that the public can understand what is going on and why it's important. So definitely an important skill in lots of different areas, including being an astronaut.
It's a very important skill.
So I guess one thing that you mentioned that I had a question of, and sorry, I'll pause. If you could please stop sharing the screen, we'll be able to see you a little bit larger on our screen. Perfect. You mentioned that impact craters can be created by an impact with a meteorite or a comet. Can you differentiate between the two? What's the difference between a meteorite and a comet?
So a meteorite is mainly made up of different minerals or rocky material and metal. That's usually what a meteorite is made of. A comet is mainly made up of dust and ice and sometimes a little bit of rocky material, but mainly dust and ice.
Okay.
And there have been some studies that scientists are proposing that can they tell if whether a crater was formed by an asteroid or a meteorite hitting the surface or a comet. So far, they haven't really found a proper way to differentiate them or to tell them apart. So at the moment, they think a comet and an asteroid can form a similar crater, and it will be very difficult to tell
Mm-hmm.
the difference.
That makes sense. Next, we have a question from Summer in Ms. Hoffman's class at Humewood Community School. Summer is wondering what would happen if water and lava were to touch.
So if water and lava touch, depending on how much, it would either quickly cause the lava, like the outer layer of a lava, to cool down very quickly, and the water would evaporate because lava temperatures can range from about 1200 degrees to about 800 degrees, depending on the type of eruption and how far it's flown from the volcano itself, because they slowly cool down as they travel further away. If you get very extreme conditions, like if magma's rising from the crust and comes in contact with water that's trapped underground, they would create what we call explosive or steam-driven eruptions. So very recently, like if you think about some eruptions that have happened on Earth, one particular recent one in New Zealand, that was driven when magma or lava came into contact with water. So it creates this explosive effect because the water is evaporated so fast that all that pressure and energies had to be released. And sometimes if it gets built up, if it's trapped underground, that's when you get those really big eruptions that can happen.
Oh, okay. I've never thought about that before. Thank you. Our next question comes from Ms. Malcolmson's class, wondering why did you choose to study lava flows and what did you do for your undergraduate degree?
I could start with the second part of the question. My undergraduate degree was in general geology. I actually studied back in Scotland, where I'm from. And my thesis then was completely different from what I did now. I mainly looked at looking at economic geology or looking at very unique minerals that mining industries can use to create different material. But I kind of wasn't really interested or very enthusiastic about that kind of topic. So when I found my master's and then PhD here in Canada, I started to realize that learning about different planets, how they formed and how the surfaces changed. For me, I found like mind-boggling and very cool. And for lava flows in particular, I picked a mixture of that was what was available for my research topic, but the fact that we can look at we found lava flows on different planets and moons, not just on our own. They've covered the surface of Venus. Moon has about 30% of its coverage is covered in lava flows in different volcanics. Mars has had the northern hemisphere and equator region is covered in different lava flows. Io, Jupiter's moon, is the most volcanically active body in our solar system, more than Earth, and it's constantly covering itself in new types of lava flows. So I just found it very intriguing that we have all these old ones that we don't really know much about except what satellites and rovers can tell us about. But we have all these new ones that are constantly being created on different moons and planets. And we still don't really know if the forces or the processes that produce lava on Earth is essentially the same that's happening on there. So I thought if we can better understand all these different types of data that satellites can pick up, studying these lava flows, we might be able to take a step closer to figuring out how they're actually forming on different bodies.
That sounds really
exciting. I hope that answered the question.
Yeah, there's so much new stuff happening as well as the old to analyze. So that's really interesting. now I have a very different type of question from Ms. Cam's class, wondering how many people's names are usually on a mission patch?
It depends on the size of the mission. Some international some international space station expeditions, and you saw the example I gave was only 3. So it's usually always have to be at least 3 to 4 astronauts. There's never just 2. There have been some space back, like far back during this space shuttle era, there were usually about sometimes 8 to 10 astronauts. I don't know if there was any that were more than 10, but some mission patches had a lot of names printed on them. But I think maybe for ease, if I'd say 3 to 4 names might be best for a mission patch.
Okay. Yes, if I understand correctly, the Soyuz is what we're currently using to send astronauts to the space station, and that it doesn't fit 8 to 10 people.
Yeah, no, yeah, it's all we have at the moment to get into the space station. So 3 people, I think, is the best. It's the maximum capacity for them.
Okay. Now I have a question from, just trying to choose which one to do next here. Bella at Humewood is wondering what causes so much methane to come from planets.
It really depends. I think the best example would probably be Mars, that they've been detecting methane gases being released from the crust, and there are 2 different reasons why that might be happening. Everyone's favorite is they think there might be some biological process that, as a waste product, is producing methane. And that's what a lot of astrobiologists really want it to be a biological process is beneath the surface as well, not happening on the surface, or be underground, or what we'd call the subsurface, that some sort of organism is producing energy by consuming some sort of material that I don't know what it is, and then producing methane as a byproduct. More realistically, what people are really leaning towards, it's a chemical process. So it could be some fluids might be passing through the ground, and again, a byproduct is methane, or it could be leftover. I can say it's not really. I don't think it would be leftover volcanic processes because there's no evidence of activity, but it would probably maybe fluids that might be passing underground. But again, no one's not entirely sure. They can only detect this from using satellites. They haven't been able to go to the ground from where this methane's coming from. So it's an open question, but there's a lot of different reasons why it could be happening.
That's always so interesting. We have evidence that it's there, and people need to now figure out where is it coming from and how is that being created and released.
Yeah, and it's usually one of these questions that drive teams to propose new missions to send landers, rovers, or attach new instruments to new satellites that might be able to better understand why this might be happening and slowly narrow down what could be causing it.
Right. So our next question is from Nico, wondering what does an underwater volcano erupt? What material comes out?
An underwater volcano. Well, if you think an underwater volcano, the largest one known on Earth, if you would call it a volcano, would be what we call the Mid-Atlantic Ocean Ridge, and it's the rift zone that's right in between North America, South America, and Europe and Africa, which is slowly increasing the size of the Atlantic Ocean. And it still produces the same type of lava that we would get up on the surface, so that doesn't really change too much. What changes is how it's actually flowing and forms when it cools. So on the ground, it's able to flow for sometimes kilometers away from its source before it starts to completely cool down and solidify. Underwater, it's in contact with water immediately. And what this creates is what we call pillow basalts. So it's essentially, as the name suggests, they create these little bulbous shapes that look like a pillow. And then new lava will break through underneath to form another one. And it will continuously keep building more until it just either the lava can't penetrate through the cooled down crust, or the eruption is no longer producing any more lava or allowing lava to keep on coming up to the surface.
It's interesting how it can be so different, but it makes sense. It takes a lot of energy to heat up water, so that would take a lot of energy from the hot lava, I guess, and it won't be able to go as far. Um, okay, we have a little bit more time. Um, Felix from Maple Ridge would like to know if lava floats in space.
Lava floats in space. It would float. Everything would float in space, so that would include lava. So if we were to just to release hot lava into space, we would just see it floating. It would cool. It would still cool down, but mainly due to radiation, because it's releasing heat still. It's just not going anywhere, so the heat would just keep being lost. But it would float. Like it's the same way you would just if you threw water into space and it would free float.
Interesting. All right, so I think I can squeeze in one more student question here. Gwen from Maple Ridge would like to know which crater is your favorite?
Ooh, so I know I mentioned in the presentation my favorite one on the moon is Tycho crater. But if I was to pick my favorite crater everywhere in the solar system, I think for me it would have to be the one I study here on Earth, which is called Mustaston Lake, and it's located in northern Labrador, here in Canada. And I think studying the rocks that have been retrieved from the crater kind of gives me more of a personal connection to that crater in general.
That makes sense. So the last questions I want to ask you are more general.
Mhm.
Wondering who you collaborate with for your research.
Well, right now, the work that I'm doing in Iceland, I'm collaborating with a professor from the University of Arizona in Tucson, United States. I've also collaborated with a couple of members from the NASA Goddard Instrument Field team. So I've gone to work with them in the field. Our deployment and their deployment was at the same time. So we were working interchangeably in the field and we shared the same campsite. In the past, I've also collaborated with other members of NASA, but from different science teams. This is when I was working in Idaho a couple of years ago. So I've been slowly been trying to write a paper with them right now. So that's that progress. And also working with the Canadian Space Agency as well. It was like if it wasn't for the Canadian Space Agency, these research projects of mine wouldn't be possible since they're funding the projects.
Right. And do you have any advice for any students who might think this sounds really cool? They want to get into either your area of research or another area of research and just sort of pursue that academic career path. Do you have any advice for them?
I would say at an early stage, if you finding something that you love in particular and looking for opportunities to get involved from as small as going to the science center to maybe finding out if there's a guest speaker near where you live that's giving a talk about space or any different STEM field. I think that's probably one good piece of advice I would give is to find to talk with different people and experts, learn also how they got into it, and you can then talk to them about what you really find interesting, whether it's what you want to get into or whether you're just generally interested in something. So I think talking around and looking for other experts, visiting science expos and guest lectures, I think is a really good way to get started.
Well, thank you so much for that. That is all the time we have today. Thanks again, Gavin, for taking the time to tell us about your research and the Junior Astronaut Initiative Patchmaker activity and for answering all of our questions.
Oh, no, of course. I was happy to give a presentation, and thank you for having me.
And for everyone who's joining us either live or watching this video recording, for more information and activities from the Junior Astronaut program, you can Google Junior Astronaut Canada and choose the web page with an address at asc-csa.gc.ca. So basically just scan for the one that's csa.gc.ca and you can navigate from there. Stay tuned for more information about webinars and other PIR educational programs at pirweb.org. And thanks so much for tuning in, everyone. I hope you have a wonderful day.